was that we defined a functional z of j, which was a constant times a functional integral of an expression of the form of d phi 1/2 phi, or x, sorry, 1/2 phi minus d squared minus m squared plus I epsilon phi of x plus j of x times phi of x. And the result was that after you do the integration, you obtain a Gaussian functional of j with the Feynman propagator sandwiched between the two j's. And then we showed that the same expression is also given by the vacuum expectation value of the time order product of exponential of the same source j times a Klein-Gordon field operator. So this was the main result of last lecture. I'm not putting 4 here deliberately. In fact, I should not even put it there, because what we are doing is valid in any number of dimensions. So there's nothing specific about 4 dimensions so far, the way that we are writing it. If instead of 4 I had put n, everything will go through. And that will be useful later on. That's the first comment. The second comment is that if you take this expression and this expression and differentiate both sides with respect to j, you will obtain, so this follows from these, that every time you differentiate with respect to j functionally, you will bring down an operator phi hat. Okay? So it will bring down, and I will differentiate with respect to 1 over I times d by dj. Let me call them yi acting on this. So this 1 over I is meant to kill the I coming from here, so that you get a neat phi hat y1 up to phi hat yn ground state, also the exponential I j phi hat ground state. And then if you do the same operation here, the only place where j appears is here, and there's a factor of I in front. So the same operation will bring down this phi on the integral side. So it will be equal to the normalization constant phi, and in the integrand you will have phi y1 phi yn exponential of the same action, the same objects. Okay?
This is the result of n times the action of that operator.
Yeah.
Okay.
If you do n times the action of this operator, you obtain this. I would like to draw your attention to the difference between this phi and that phi. I'm denoting both of them phi, despite the fact that I'm writing them slightly differently. So I'm putting a hat on the left-hand side, I'm not putting any hat on the right-hand side. The phi's standing on the left-hand side are field operators. They do not commute at different times with each other. Of course, they commute with each other at the same time, but not at different times. So the time ordering here is important. On the right-hand side, there is no time ordering, and these phi's are not any operators. They are just ordinary functions. So you can put them in any order you like. I have written them in the same order that I have written it on the left-hand side. But I could have easily put that one in the middle or in the first place and this one last place. These are just ordinary functions, so it doesn't matter in which order you put them. They are integration variables. In fact, I could have denoted them different letters, not phi. I could have put them chi of y1, y, etc., etc. It's just I'm just integrating over a variable. Okay? So the result, the conclusion is that the functional integral automatically produces vacuum expectation value of the time-ordered product of operators. It doesn't produce just vacuum expectation value of the product of the operators, but time-ordered product of the operators. And there's a big difference between the product of operators and time-ordered product of the operators. In fact, historically, one of the important steps in the development of quantum field theory was the invention of this time-ordered product. Right? It played a key role in developing covariant perturbation theory. So this is important to keep in mind, that the functional integration produces automatically the time-ordered product of expectation value of the time-ordered product of operators. Okay? And the final remark about last lecture is that we obtained an expression for this n, which is basically obtained from the fact that if you set j equal to 0 on both sides of, for example, this relationship, you see that z is 1. Or if you set j equal to 0 here, you see that j becomes equal to 1. Or here you set j equal to 1. So if you put it here, then n inverse will be given by the same functional integral, except that this term will be absent. Means, so if I remove the n from here and write it explicitly, it will be the same functional integral times exponential of without these arguments. It has to be like this because of essentially because the vacuum time vacuum is 1. We have assumed that the vacuum is normalized. Okay? This clear? So this is essentially what we learned last time. Any questions? Today we want to move on and go to the next step. Obviously we don't want to stop here. This corresponds to a free field theory. We would like to put terms different from quadratic in the integrand so that we produce a theory which is interactive theory. So for that reason, I'm going to shorten the notation and call this part of the action, I'm going to call it I05. And then consider, I'm also going to, I put a 0 there, the subscripts, which I'm going to drop today. So today we are going to define a z without the subscript 0, but still it will have a constant which I will call for time being n prime, and very quickly I will remove that prime from n. But the exponent will be this time I05 plus a term we will call I interaction of phi plus I j phi, where I interaction, let me put I0 here so that you know which part we have in mind. So I0 is dx 1/2 phi minus d squared minus m squared plus I epsilon phi. It's just a bilinear part of the action. That's I0. I interaction, on the other hand, will be anything which is different from a bilinear, because the bilinear part has already been written here. So we will take it to be you can take it to be g times phi. In this example, we will take it to be just polynomials in phi. I want to put minus sign in front of this so that in the Hamiltonian everything comes with a positive sign. You can add whatever you like. Okay? Polynomial in phi. And this object here will be called L interaction phi. Okay, so we would like to see how we can evaluate an integral of this type. As in there, eventually we will not evaluate any integral at all. We will just manipulate the relations in such a way that the result will simply come out. Okay? Now, actually we can do this for the following reason. In the integrand, we have exponential of I times dx li, which is a polynomial. This is, and then we have this term. These are commuting functions, and I can separate the exponentials from each other without caring about their order. Okay? If they were operators, you couldn't do this in this way. Okay? But with the ordinary functions, of course, you can do them. Let's assume that we have expanded this, the first exponential. If you expand it, it will be 1 plus I dx phi plus 1 over 2 factorials I squared, the same thing to the power 2 plus dot dot dot. If you expand, you will get all these terms. And then we have this other term, exponential of I j phi, standing there. Okay? So, we will consider each term in turn. Obviously, 1 times that gives you 1, it gives the same exponential, so we come here, and here, let's just consider this first term, minus g times phi in the Ly. You see that this times exponential, eventually everything is multiplied with exponential. This times exponential can be written as minus g 1 over I d by dj times exponential. If the d by dj acts on this exponential, it will bring down a factor of phi, and that's what we want to have here. And I put 1 over I here in order to kill the I from there when you differentiate. Okay? This is a simple thing that I am writing. Right? If you go to the next term, which is phi cubed, the same operation will work, except that you will replace phi again by 1 over I d by dj to the power 3. If you differentiate 3 times this exponential with respect to j, it will bring down the phi cubed. You can repeat this on all terms standing here in Ly, and then you can repeat the same thing in the next term and repeat the same thing in the next term. And therefore, the whole thing that we have here will be Ly, evaluate that 1 over I times d by dj. That means you can erase this and write this expression as exponential of I dx li for phi replace 1 over I d by dj, acting on the same exponential. Because every time d by dj acts on this, it replaces d by dj by phi. Am I clear? Any questions? we will use these such tricks quite a lot. So it's better to learn it the first time, or if it's not clear, I can explain again. Okay? But do not miss the point. This is something that is very useful, and it will be used repeatedly. So nobody has questions on this. Okay. So therefore, I'm going to raise all these things and replace this I interaction as a functional of phi. In that functional, I will replace it by 1 over I d by dj. So let's just remove this line, and go back here, and write this expression as integral over phi exponential of I 0 phi, and here let me write it as I interaction 1 over I d by dj times the exponential of j phi. Okay? But now you have achieved something, because this factor here does not depend on phi. We are integrating over phi, and this is a differential operator with respect to j. There is no phi dependence here. So we can take it outside the integration sign. And the leftover integral must be recognizable to you. So what's this? Z0. That's exactly this integral. So if you substitute the first term by I0, this integral is exponential of I0 phi plus I j phi. It's actually, we have this integral there, therefore it is z0 divided by n0. So this is 1 over n0 times z0j. It's a functional of j, but we know what kind of functional of j it is. It's a constant functional of j. So this is a constant. Together with n prime, we are going to call it n. N is the ratio of n prime to n0. It doesn't matter what it is, because these things will cancel over at the end. But if you want to know what it is, that's what it is. Okay? And we know what kind of functional that is. That's this. We have it here, there is it here. Therefore, the result is that z of j equals to n exponential of I, let me call this dy L, in which phi has been substituted by j, d by dj, acting on a Gaussian. We integrated this highly complicated integral and obtained this. Differentiation is something that everybody knows how to do. Integral is not like this. Integrals can be very complicated, and we know only how to evaluate integrals exactly for a small number of integrals. But there's no function that you do not know how to differentiate. Any function given, you can differentiate. Okay? So we turn integration into differentiation, and thereby obtained the solution to our problem. Our problem was to evaluate that integral, and the solution is that integral is given by the derivative of this function R, Gaussian function. Okay? Questions? Now, this is a closed form of the result of that integration. But it's not very useful because this function R is very complicated, this one. And when you expand it, as you saw, there are plenty of terms. In fact, the only way you can evaluate it exactly is to expand and differentiate term by term. And that is not manageable because there are infinite number of terms. You have to keep the combinatorics and all that. So you have to invent clever ways of doing it. And that's precisely what the Feynman graphs will do for you. But before moving there, oops, I should have not erased this. Let me tell you one more thing, then we will go to the graphical way of evaluating that point. So, this was one expression for Z0. For Z0, one expression was this. The other expression was that it was a vacuum expectation value of time order product of exponential of Klein-Gordon. So therefore, the same expression Z for Z, the same expression, I mean this one. So this is Z of J, I mean this expression. Okay? You have a Z0. Putting there any form of Z0, you'll obtain a new way of writing the same thing. But this time, I would like to write it in this way. So there is an M prime there. There is exponential of I interaction. Let me put just, well, I looks a little bit silly, so I'm writing it like this. 1 over I d by dj. For Z0, this time we would like to put vacuum expectation value of exponential of I j phi hat. Okay? That was another way of writing Z0. Now again, I can do the opposite operation, namely push this inside the vacuum expectation value. It's a differential operator. It has no phi hat in it. It can go through everything and sit inside or keep outside. It doesn't matter. But it is neater to push inside and write the whole thing as time order product of exponential of I interaction 1 over I d by dj exponential of I j phi hat ground state. Okay? Now we can actually operate on this object. Every time it hits the exponential, j 1 over d by dj will be replaced by phi hat. Therefore, we have exponential of I. Let me write it in the original form of Li, and this will be replaced by phi hat times exponential of ij. Phi hat ground state. Expand in powers of j both sides, or differentiate with respect to j n times to see what we get. So take this and act on it d by dj x1, I d by dj xn, z of j. This will tell you every time that you hit by d by dj, the only place where it actually is. There is no j here, therefore it will bring down a factor of 5. So it will be phi hat x1, phi hat xn times exponential of I d by ni phi hat grams. This is the function we are going to call, we are going to give a name to it. This is in fact the endpoint functions that I started my lecture yesterday by telling you that we are interested in these functions. However, yesterday I told you that we are interested in these functions which were defined in terms of the ground state expectation value of the time order product of Heisenberg field operators. Today I am getting an expression for it. If I set j equal to 0 here, I've already set j equal to 0. So let me set also the j equal to 0 here. I am getting an expression for it in terms of the vacuum expectation value of the free Klein order fields. Actually, these fields are the fields in the interaction picture. You know that interaction picture, the field operators satisfy free field equations. This phi satisfies free field equations. That's the definition of the interaction picture. And the operator sitting here is, you have seen it in the previous term. Is what? It is the S operator, S matrix. The S metric is the time order exponential of minus I times the Hamiltonian, interaction part of the Hamiltonian. For this model where there is no, it's just a polynomial, interaction Hamiltonian is minus I the interaction Lagrangian. And that's precisely what's here. So this is, in fact, minus I interaction Hamiltonian. Okay? So what we have obtained is that the endpoint function is, I haven't still shown you that this is the same endpoint function as we introduced yesterday, namely the time order product for Heisenberg field operators. But I am getting a function of n x's simply by ground state expectation value of these free field operators times the S operator times the ground state. Okay? It's clear? Not, huh? Is it clear?
Yeah, it's clear. I was stuck in the part where you introduced the exponential to the time order product, and the two exponentials are product.
You mean here?
Yeah.
So from this step to this step.
Yeah. Why is that the exponentials got inside the other exponential instead of?
There is no phi in here. There is no field operator phi.
Yeah.
This operator can go inside the expression.
Yeah, but how do you
see that?
how do you operate the both exponentials by introducing the other exponential inside the first one?
It's not inside. This exponential. This is exponential of this times the exponential of that.
Ah, okay. The brackets are outside.
I'm sorry if it is. So I should have. I thought I'm saving space, but actually I'm not. So let me write it. There's more space if I'm not using it. Exponential of I interaction 1 over I d by dj acting on it.
Okay, and the problem was the second bracket, the one.
I should have put it here.
Yeah.
The time
Yeah, that's.
Sorry for that. But this line is clear.
Yeah.
Or is it not?
Yeah, it's clear. The rest.
Okay. Other questions? Stopping for such notational sloppiness on my part, okay? Please. Okay, now just to complete this line, let's come back here and note that I'm differentiating z with respect to j n times. So I might as well do it here. If I do that, again I bring n factors of phi. So the same expression is given by a normalization factor times functional integral of a string of n factors of phi times exponential of, if I have set j equal to 0, the only thing which remains here is just I of phi. I of phi is the sum of these two i's. So I of phi is I0 phi, is the total action, plus I interaction phi. Okay? So again, the functional integral, even in interacting theory, gives you the vacuum expectation value of the time order product of field operators. How do we link all this to the endpoint functions of the Heisenberg operators? These are the Klein-Gordon operators. The answer you will find by solving the following exercise. There are two ways of doing this. One way is the one that you will find in most of the textbooks, and the other way you will not find in most of the textbooks, maybe some, but not most. The first one, which is the common way that you will find everywhere. You go back here and go back to the definition of the S operator. So I said that this thing here is the scattering operator, S hat. It is actually the definition of scattering operator. Okay? So the exercise for you is the following. I'll just put it in the form of exercise because I assume that most of you have seen these things. Use the definition of time ordering to show that the Gn, which we defined in this way, is in fact time order product vacuum expectation value of the time order product of Heisenberg field operators phi hat x1, phi hat xn on the ground, Heisenberg ground state divided by what? Divided by nothing. Just this. Okay, so you are asked to show that the G that we defined, the G there, is given by this expression. In order to show this, you have to make a transition from interaction picture to Heisenberg picture and show that that expression goes to this one. This is something that you will find almost in every textbook. Okay? This is just going from interaction picture to Heisenberg picture or vice versa. The second exercise is the one that will prove the same statement, and which I like more, is this one. Like in the free case, define a function z prime j as the ground state expectation value of the exponential of the Heisenberg operator times Heisenberg times j. It's a definition. In the last lecture I gave you an exercise exactly like this, except that I had a 0 here and this was the free field operator. Now we would like it to be Heisenberg field operator. Now that exercise asks you to take the derivative of this object 1 over I dz prime by dzj evaluated at x, and act on it by d squared minus m squared, and then on the right hand side there was a term. I don't know if you have looked at that exercise. Okay. Now take this and obtain an equation which should be the generalization of the equation you obtained in that exercise for the same object. Obtain an equation for this. For 1 over I dz prime by dj. Okay? And then show that the z that we have here satisfies that equation. And show that z of j given by star satisfies that equation. Is the exercise clear?
That's a star.
Z star is this. That's the equation. You should show that this object satisfies the equation that you obtained for z prime, where z prime is defined in this way. And the result will be z prime should be the same as z. Right? So, you have line. So the result of creation of exercises, this is 1 and this is 2. 1 and 2 will tell you that z prime of j is the same as z of j. In other words, there is a single z which is and it's the same as in order to avoid that misunderstanding, let me write it like this. Actually, I call that operator S hat, so let me call it S hat times exponential of phi j phi hat. there is a subscript H here, which indicates Heisenberg, no subscript in here, which indicates free Klein coordinate. This is the way I distinguish the two things from each other. This one is the Klein Gordon ground state, the free field ground state, that's Heisenberg ground state. This proof, the second proof, essentially tells you that there is no distinction between the two ground states. In the first proof, you have to make some argumentation to how to you relate the two ground states. If you take the derivatives of both sides with respect to j, or expand both sides in powers of j, and identify the coefficients, from here you see that the endpoint functions, the left-hand side will tell you that given by and the right-hand side, of course, will be given by and this helps us to tell what this normalization factor should be. Because if you put n equal to 0, here you will have no operators. So you will just get ground state times ground state. On the other hand, on the right-hand side, you will not get ground state times ground state. You will get something else. So, normalization factor n prime set n equal to 0 in equation W star. This is our equation W star. The left hand side is just this. And the right hand side is S hat times ground state. But this is 1. This is 1. So this is telling us that n prime equals to S hat to the power minus 1. And therefore, the final result which we are going to use is this formula sometimes in some books is called Gell-Mann-Law formula. But the naming is not universal. I mean, for example, Feinberg doesn't call it Gell-Mann-Law formula. Also, he makes a comment that it was known to them. This is the key formula in quantum field theory because it's telling you how to calculate the things. And the Feynman graph is basically rewriting of this equation in graphical form, as we will see in a minute. Any questions? So this is one of the main results of the last two lectures, the previous lecture and today. Okay? And with this, for a while, our manipulation of functional integral is coming to an end. From here onward, we will do other things. We will not evaluate integrals. So if you have any question on the topics that we discussed so far, this is the right point to ask.
What's the difference between the Heisenberg vacuum and the usual?
Yeah. a phase. When there's no external fields around, they are related to each other. They can differ only by phase. These are the in-fields and in-states. The in-fields and in-states, although they are very similar to the interaction picture, but they are Heisenberg field operators and Heisenberg states. And therefore, the in-state is the in-vacuum, is a Heisenberg vacuum. Okay? But the reason why I'm giving you the second exercise is in order to bypass that discussion. The asymptotic conditions, etc., etc. These are tricky things when you write in terms of operator formulation of quantum field theory. But doing in a way of solving differential equations, somehow you bypass that. You do not need that discussion. You just show in one go that this identity is correct without paying too much attention what's the difference between Heisenberg ground state and the perturbation theory ground state, or the in-ground state. If you are familiar with the formulation of perturbation theory in terms of in and out states, I don't know if Johan did it that way. In the old-fashioned perturbation theory, where you do the interaction picture, these distinctions are rather obliterated. But in terms of the more modern, I can't call it modern, in terms of in and out fields, etc., then if you understand that the in states, the in fields, out with all Heisenberg operators and Heisenberg states, then the distinction is not so important. I mean, you see that they are the same. Well, I want to bypass that discussion. That's the reason I went through this way. Because it is, in my opinion, not very useful, for practical reasons, it's not very useful. This is the starting point of the practical calculation. Other questions? So, what are we going to do with this now that we have obtained it? The idea is, of course, to calculate it. And you have, in principle, a machine to calculate these objects. Now that we have proven this is equal to that, and everything equals to this is the functional integral, and we have an explicit expression for this, because if you put this outside, then it will be this operator acting on a Gaussian of J. So you can differentiate, obtain Z to any order, then differentiate Z with respect to J and obtain the endpoint functions. Everything becomes differentiation. Everything, okay? The whole calculation of these Jn becomes differentiation of a Gaussian of J. This is straightforward, and conceptually there is no problem with it. But in practice, it's tedious. You can examine, you can try to calculate some lowest order terms, lower order terms, and you see that it will take some time, this differentiation. Although it's trivial conceptually, but practically it is tedious. The other way is to convert the whole thing into a set of diagrams with well-defined rules, and whatever you want to calculate, just draw the diagrams and apply the rules and calculate diagrams. Even that one is not simple, because if you go to higher orders, there will be plenty of diagrams. But still, for lower orders, especially to get some physical insight about some processes, it's more useful. Okay? So let's learn how we go from here to diagrams, diagrammatic representation of these objects. I haven't yet told you why these are interesting things. We will see that these are interesting things because you can write a formula which links directly these expressions to the elements of this scattering matrix. So given any process that you want to calculate the matrix elements of a SAT, the scattering matrix operator, you can just act on these functions by some differentiation. Again, it will be differentiation, but again, those things will be reduced to evaluation of final results. And we will come to that point later. For the time being, let's see how this machine is functioning, how we can actually evaluate the things that we wrote there. And then later on, we will see how we can extract physics from these objects. So far, I have not spoken about any physics, actually. All we have done is to define some functions and obtain some formula for those functions. We have not even evaluated those functions explicitly. Okay? The evaluation should be clear here. Because since this equals to the right-hand side, and in the right-hand side you have only free fields, you can expand the S hat in a power series, and then in each term you have the time order product of free fields sandwiched between ground states. What do you do with that? The next step. If you have the matrix element, if you have the time order product free fields sandwiched between ground states, how do you evaluate that? Apply Wick's theorem. So apply Wick's theorem and convert these expressions into the sum of products of final propagators. That's the meaning of Wick's theorem, to convert the time order product of objects into sum of products of final propagators. So to see how it works, let's just look at an example with a specific Li. The example I have chosen here corresponds to, so this is an example. The idea is, first of all, Feynman diagrams. So take Li to be, just as an example, phi cube. And calculate the right-hand side up to lambda squared from here. Let's first look at the denominator. So in the denominator we have S hat, which is time order product of exponential of I, let's call this dy. Let me just, okay, Li phi hat. For the example that we have, it's exponential of minus I lambda over 3 factorials dy phi hat cubed. Why? The best you can do is to expand. It's 1 plus minus I lambda divided by 3 factorials dy by cubed y plus 1 over 2 factorials minus I lambda over 3 factorials to the power 2 dy1 dy2 y hat cubed y1 hat cubed y2 plus infinite number of other terms. So we are going to sandwich this expansion between two ground states and evaluate term by term. So our aim is to find this. That's the denominator. Okay? So let's call this equation A. First thing is to evaluate the denominator of A. So the 1 obviously will give you 1. Then the next term is minus I lambda over 3 factorials dy ground state time order phi cubed y ground state plus other terms. What's this? 0. We also mentioned last time the product of odd number of fields will give you 0. You can sandwich between parentheses. This one, we have to calculate. Okay? To calculate, we have to apply Wick's theorem on this. That's the only thing you need to do. So, up to this order, the only thing you need to calculate is this. How do you calculate such things? How do you calculate? What's Wick's theorem? So you contract them pairwise. So you write them as phi 1, phi 1, phi 1. This stands for these ones, and phi 2, phi 2, phi 2. Okay? And contract them in all possible ways. Okay? If all of you know how to do this, then I will not spend any time on that. Is there anyone who doesn't know how to do this? So you all know. Okay? Therefore, I'm not going to spend any time on that. I've given a quick explanation in the notes, but I think since all of you know that, let me just write the result. The result is 3 times 3 times delta Feynman squared evaluated as 0 times delta Feynman y1 minus y2 plus 2 times 3 times delta Feynman cube y1 minus y2. So can one of you tell me where does this 3 times 3 come from?
Quadratic phi 1 with a phi 2, phi 2.
So it comes just all possible ways of contracting these ones with this, with the condition that, where does this come from? Which contractions give you this? So if you contract among this set, among the fields in this set, it will give you just delta Feynman at 0. When you contract one from here, one from there, it gives you that term. Okay? With 2 different arguments. Likewise in the lower one, there is no set contraction. Therefore, you get only that. Good. So when we substitute here, then so we said that there is a 1 there, the first order term disappears, and you have 1 over 2 factorials minus I divided by 3 factorial to the power of 2 delta y1 delta y2 times 3 times 3 plus 2 times 3 Okay, so the prefactors simplify. The numbers simplify, and at the end, let me just remove these numbers and keep whatever survives. Obviously, minus I lambda to the power 2 will survive from there. The coefficient in front of this becomes 1 over 8, and this coefficient becomes 1 over 12. So the way we represent them is with each delta phi from y1 minus y2, we will associate a line going from point y1 to point y2, and then there will be a vertex which should be associated with minus I lambda. And therefore the first term, this one, there is point y1 and point y2. There is a line which is joining them. How do you represent this one? This factor? It starts from one point and goes back to the same. And there are, in fact, if you had looked at them, one of them comes from, for example, this contraction, and the other one comes from this contraction. So one of them gives you a loop at that point, and the other one gives you a loop at this point. Okay? From each vertex, there are 3 lines going out. Likewise, the second term, this is the 1/8 term, and the second term so the rule is that from each vertex we have as many lines going out as the power of phi in this interaction Lagrangian. With each vertex we associate the power of the coupling constant. So there are 2 vertices here, therefore there will be minus I lambda to the power 2. With each vertex we associate minus I times the coupling constant. There are 2 of them there, therefore minus I lambda to the power 2. And then there are numbers in front. So the Feynman graph basically has 3 aspects to it. The first one is to obtain the Feynman rules. The Feynman rules can be read directly from the Lagrangian. Given a Lagrangian, we can define the propagator and the vertices. The propagator is always the inverse of the differential operator, which is sandwiched between the 2 phi's. Okay? You look at the quadratic part, there is differential operator sandwiched between them. You take the inverse of that, in our notation, multiplied by I, and add plus I epsilon in the denominator. That gives you the Feynman propagator. That's this one. The vertex comes from any part of the action or the Lagrangian which is not quadratic. It could be first order, just phi cubed, phi to the 4, etc., etc. From each vertex, as many lines will go out as there are fields in that vertex, in that part of the interaction Lagrangian. Here, there are 3 fields, therefore 3 lines go out from each vertex. Then you connect these points and by lines, by the propagators to each other according to the rules. Follow the rules and construct any graph that you can construct. The impressive thing about the Feynman diagram technique is that any graph that you can construct following the rules will correspond to a term in this matrix. And of course also any term in this matrix can be represented by a graph. So there is one-to-one correspondence between the graphs and the terms in this matrix. The only tricky part is these prefactors. You have to know what's the prefactor, the so-called symmetry factor associated with every graph that you have drawn. Okay? And the second thing is that make sure that you don't forget any graphs. So if you go to a little bit higher order, the number of graphs becomes very large. If you do that way, the number of terms in this matrix will be very large, and therefore you may miss some graphs. So make sure that you don't miss any graphs. Drawing the graphs themselves is not difficult. The part that needs a little bit of thinking and working is this symmetry factor that you have to figure out correctly. And that will be left as an exercise to you. I've given you some exercises in which you have to work out the symmetry factors. I will also ask the assistant to, if you don't know how to evaluate those things, to explain to you how you can read out these symmetry factors. I assume most of you know that. Huh? But in any case, it's not difficult it's not difficult at all. You can just learn the rule and calculate the symmetry factors. But I don't want to spend time on the blackboard because we are not going to, in practice, to use it in the rest of this lecture. But it's important to know that, how to calculate these numbers. Okay? This was the denominator of the expression here. The graphs like this, which have no external lines, they are not connected to the external points x1 to xn. These are called vacuum bubbles. And they come in the denominator of the expression we are interested in. The main part, of course, comes from the numerator. So this was the denominator. Denominator of equation A. This is equation A. Is given by this expression or by this graphical expression. Now we have to work out the numerator. The numerator is, of course, you will work out in the same way, except that you have to stick in the product of the operators in here. So we will take the example of n equals to 2 and work out the numerator. Means we have to evaluate so essentially, like here, the basic element that we need to evaluate is to apply Wick's theorem to the binomial. Well, there is, of course, the first term when you expand plus 1 over 2 factorials minus I lambda over 3 factorial d by 1 d by 2 Again, we have to contract. Okay? We have to contract everything in all possible ways. So this is just Feynman propagator plus the rest. The rest again can be expressed graphically. Since all of you know how to do these things, I'm not going to explain the prefactors and all that, but we'll draw the graphs. So basically there will be 3 graphs. Okay, I'm not going to write the deltas. I will just put the numerical factor in front, remove these things, and keep minus I lambda. This is the workout expression. Okay. This will multiply I'm putting the notation 1 bar, 2 bar, 1, 2, 1 bar, 2 bar. So the barred indices are x's. The unbarred indices are y's. We are integrating over unbarred indices. So x1 is 1 bar, x2 is 2 bar, y1 is 1, and y2 is 2. You integrate over these points, and these are x1 and x2. This is one graph. That means the result is the Feynman provocator times the provocators corresponding to this one. The expression for this, for instance, is delta of x1 minus x2 times delta of y1 minus y2 to the power 3. There are 3 provocators to the power 3, and delta of x1 minus x2. That's the expression corresponding to this. Okay? Plus one over 8 times again the Feynman provocator, 1 bar, 2 bar, but this time it will multiply this vacuum part. Again, it will be this times this one. This one we already wrote here. And finally, there is one more term. At this order, which has no vacuum bubble in it. And its prefactor is 1/2. So in the integrand, you have the sum of 3 terms, this one, this one, this one. With each one of them, there is an algebraic expression that you can write down. For example, this one corresponds to that algebraic expression. For this one, you write delta x1 minus x2 times the expression corresponding to that, which we gave here. And this one is delta of, this is 1 bar, 1, 2, 2 bar. Delta of x1 minus y1, delta of y1 minus y2 to the power 2, delta of y2 minus x2. It's clear? Have a question? This is numerator. We have the denominator, we have the numerator. To obtain the exact, the expression of the lambda squared, you have to divide the numerator by the denominator. Okay? That will be the final result. Are you with me or you have lost me? You are following me? So you have to divide them. We are calculating G2 up to the order lambda squared. So G2 up to lambda squared order will be, I'll just write the graphs in the denominator and numerator and tell you what happens when you divide them. So there is this one, the first one, I could also make the prefactor. Sorry. Before that, there is this one, that's the leading order term. Then there is minus I lambda R2. The graphs are 1/12 plus 1/8 times plus 1/2 times this. This is everything which stands on the numerator. That term plus all these. In the denominator, on the other hand, you have 1 plus 1/8 of this plus 1/12 of that fellow. And the coefficient in front of this one is also minus I lambda to the power 2. The result of that calculation up to the order of lambda squared will be that ratio. Okay? So we have to obtain a final answer in the form of something plus lambda squared times something else. That will be the final result. For that, you have to expand this denominator and multiply with the numerator. And in the expansion of the denominator, you should keep only the terms up to the lambda squared term. So if you expand this, it will be 1 minus this expression. And then you must multiply that with this. So what will happen? If you take 1, if you multiply this by the same expression with the minus sign here, you have to multiply term by term. That's the term over to 0. You multiply the term over to 0. So that will give you, I'm going to write the result here. So G2, which is prime order product of the Heisenberg operators with x1 and x2 up to the order of lambda squared. One term will come the zeroth order term is the product of that term with this. Obviously there is no other term, so it will give you delta f x1 minus x2. Then the coefficient of lambda square terms. Here you have plenty of terms because the zeroth order term can multiply this, will give you lambda squared. The lambda squared from here can multiply that and give you a lambda squared. The zeroth order term multiplying this, we should remember that the factor here, the sign should change. It should become minus. It will be that term that times this propagator with the coefficient 1/2 with the minus sign in front, but then minus I lambda squared. Here you have precisely the same term, but with sign plus. So the product of that propagator with this will cancel this term times 1. Okay? The product of this term with this will produce precisely the same term with the same coefficient, of course, but the signs will be opposite. So they will also cancel. Finally, the only thing which will be left will be this lambda squared terms times 1. That means all this part goes away. And what remains at the end is 1/2 of this graph. No vacuum, disconnected vacuum bubble. If they didn't go away, you would have disconnected vacuum bubbles like this. This is a graph with 2 external points, but a vacuum bubble which is disconnected from the external points. In the ratio, the vacuum bubble disappears. Is this a phenomenon which happens only to this order in this particular model, or is it general? Graphically, it is trivial to see that it's in fact a general phenomenon. That means there are all of the denominator in our expression is to cancel all the disconnected vacuum bubbles. Okay? It's very easy to see that. You can prove it also algebraically, but graphically it is more or less obvious. Let's assume that you want to write this to arbitrary orders, in fact to all orders. So all you do is to draw all possible graphs. Right? So I'm going to classify these graphs in the following form. In the first line, I'm going to write all the graphs which do not have any vacuum bubbles. Like this one, and like this one. So they will be graphs like this. We will not worry about the p-factors because you will see that they will take care of themselves automatically. I'm not going to draw all the graphs, of course, but we will give you some in order to clarify the idea. And then plus infinite number of others. Okay? In the second line, this is not the end of the story, because when you expand the numerator, there will be also graphs which have disconnected vacuum bubbles, like this one. But all of them can be obtained from the whatever you have written in the first line times the expansion of the S operators. They come all from contraction of the operators among themselves, which do not contract with the external points. The source of this denominator is exactly like the numerator, except that the operators coming from the interaction Lagrangian have been contracted among themselves. They didn't care about the external points. Therefore, in the second line, we can repeat the first line. Not like this, sorry. I want to take in one go the ratio. So we have to divide the numerator to denominator. And it's skipping some points, okay? But it should be clear. So you will expand the numerator and you expand the denominator. Okay? In the numerator, first I am writing all the graphs which do not have disconnected vacuum bubble. Then there will be graphs of like this one multiplying the vacuum bubbles. They will contribute also to the expansion of, write all of them. Whatever graph comes out from the expansion of the denominator. In the next line, I am going to take this one and repeat the same thing. I am writing the numerator, no? This is the numerator. Numerator of G2. And take the next one, all of them, whatever you have in the first line, when you multiply it by all possible vacuum bubbles, you will generate all the graphs which can contribute to the numerator. Am I clear? But what are they? So what is inside this bracket? Inside this bracket is exactly the expansion of the vacuum expectation value of S hat minus 1, because the 1 is missing. The 1 times 1 has produced this term. The 1 times the numerator has produced this term. So it's not going to be repeated here. If I put 1 there, then I should have dropped that term. Right? So what's standing here is, in fact, that expansion minus 1. Likewise, what's standing here, what's standing here. Okay? So you see that we have to take the sum of all these terms. Right? And a factor of S then so from all these terms you will generate a factor of S times these graphs from this S hat times other terms, and that factor will cancel the denominator and you will get only the graphs essentially in the first line. Is clear? So graphically it should be clear that when you divide by the denominator you will get only, I'm not saying you will get only connected graphs, mind you, keep in mind. I'm not saying that this will eliminate disconnected graphs. This will eliminate only disconnected graphs which have vacuum bubbling. That means they have a component which is not connected to the rest of the graph and it's entirely vacuum bubble. Okay? So for example, if you look at the 4-point function, as an example, this is a 2-point function. If you look at the 4-point function, G4, there will be following type of graphs. So if you look at G4, this is a contribution to G4, the product of two Feynman propagators, and this is a disconnected contribution. That will not be eliminated by that ratio, because this doesn't have any vacuum bubble. Or this is a contribution to G4. Each one of them is a lambda squared term. If you go to lambda to the power 4, this will contribute to G4. Of course, there will be also a contribution like this, which is a one-piece connected 4-point function. But there will be also contributions like that, and they're disconnected, but they do not have vacuum bubbles. So they will not be eliminated by dividing by the vacuum expectation value of this matrix. Okay? The graphs which should be disconnected are the ones, the graphs which should be cancelled are the ones which have the vacuum bubble, disconnected vacuum bubble. And all over time. So let me stop at this point.